Energy is one of the central concepts in physics. It shows up in almost every theory and proves its value time and time again. As you are aware, there are different types of energy, each with its own formula. You probably already know kinetic energy as describing the energy related to motion, which is 1/2 times the mass of an object multiplied by its velocity squared. You've probably also encountered gravitational potential energy, which can be written as the mass multiplied with the gravitational constant g times its height. And there are of course numerous other forms of energy. You might have encountered electrical energy or magnetic energy, perhaps nuclear energy, and of course there is the rest energy E is equal to mc squared. What makes energy such a powerful concept in describing reality is arguably what is the most important law in physics, namely conservation of energy, which says that for a closed system, the total energy will always be the same. So in other words, it remains constant over time. Now for all the benefits that this concept of energy provides, there is one major downside, the elephant in the room. Energy is not really something you can point at. It's not really tangible at all. If you were pressed to say what energy exactly is or point at it in the real world, you'd probably have quite some difficulty doing so. Now, what is very tangible, on the other hand, is an object and how it moves through space, or in other words, motion. If we have such a moving object, it has a position in space and a velocity, which basically tells us how the object's position changes in time. What we will do in this video is to reformulate the concept of energy in terms of motion, actual and potential motion. And by doing so, we might even be able to replace the concept of energy altogether and only look at the world in terms of moving objects or in terms of motion. And to do this, we will first show that conservation of energy is nothing more than a statement on the kinematics of an object by using some very standard mathematics. And then we will interpret the result that we get and make it more tangible by looking at a concrete example. So with that said, let's get right into it. And to show that the law of conservation of energy is a statement about the motion of objects, what we're going to do is we're going to derive the formula for the conservation of energy from the most fundamental formula for motion, which are of course the kinematic equations. So of course we start with writing down the kinematic equations that we know. And the first one is the most general one. It's that x of t is equal to x0, the initial position, plus v0 times t, plus 1/2 times a, the acceleration, times t squared. And this will be the first ingredient that we will use. And there is of course the second equation of kinematics, which is also oftentimes used, which says that v of t, so the velocity after a time t, is equal to the initial velocity v0 plus a multiplied by t. And we will now use these two building blocks, which are basically mathematical statements on how the position and the velocity changes if we have an acceleration, to derive the conservation of energy. Now the first thing that we're going to do in this regard is try to get rid of this a, this acceleration in this first equation. Now we see that we also have an acceleration a in the second equation. So what we're going to do is to rewrite this second equation such that we get a formula for a, or isolate a to one side of the equality sign. This is a very basic algebraic operation which gives us that a is equal to v of t minus v0 divided by the time t. And I'm also going to draw a box around this equation because we will be using it later on. And as we said, we now have an expression for a, which we will now fill in our equation 1 in order to get a new equation. We get that x of t is equal to x0, we just copy this, plus v0 times t, which we can also copy, plus 1/2 multiplied by this a, this acceleration. But we now know that this will be this expression right here. So 1/2 times v of t minus v0 divided by t multiplied by this t squared, of course. Then we immediately see that we can cancel this t in the denominator with 1 power of t in this t squared. And this equation can be rewritten by doing the following. We simply copy x of t, which is x0 plus v0 times t, plus the first term in this bracket, which is 1/2 times v of t multiplied by t. So we get plus 1/2 v of t times t minus 1/2 times v0 times t. And we see that we have a v0 times t here, a minus 1/2 times v0 times t here, so we can subtract these two, and this x0 we bring to the other side of the equality sign. And this brings us to our preliminary result. We have x of t minus x0 is equal to 1/2 multiplied by v of t plus v0 multiplied by t. And this equation already starts to look a little bit like conservation of energy. Because on one hand of the equality sign, we have terms with a velocity v, and we know that the kinetic energy is proportional to a velocity v. Well, it's v squared, but we'll get there in the end. And on the other side, we simply have terms that have the position, and we know that the potential energy is exactly proportional to the position of a particle. However, there's one thing that we don't have in the energy conservation law, which is this t, this time variable. So we want to get rid of this t in this formula somehow. Now remember that at one point I said that we will be using this equation right here, and this is exactly that point. We're going to swap this t with this a right here, which is just multiplying and dividing, so it checks out. And that will give us a formula which says that t is equal to v of t minus v0 divided by the acceleration a. And that one we can now in turn fill in our equation. So let's do that right now. So we can rewrite the result that we had as x of t minus x0, which is just copying. And this will be equal to 1/2 multiplied by v of t plus v0 multiplied by this t right here. But now we know that t can be rewritten as this term in terms of the velocity and the acceleration. So we do just that, and we multiply by v of t minus v0 divided by the acceleration a. And at this point we see that we have v of t plus v0, and here we have v of t minus v0. And then we use our knowledge of algebra that a plus b multiplied by a minus b is equal to a squared minus b squared. And therefore we can rewrite the right hand side as follows. We have 1/2 times 1 over a, because this 1 over a can be put outside of these brackets. And then we simply have v of t squared minus v0 squared. And now it is really starting to look like the conservation of energy, because we now have this v squared, which is indeed in the formula for kinetic energy. So to bring this home, we're going to do the following. We're going to identify all of the terms in this equation which depend on this variable t, which represents the position and the velocity of an object at a specific time t, and we're going to bring it to one side of the equality sign. And then we're going to identify this initial position and initial velocity, which are the position and velocity of the object earlier in time, and bring them to the other side of the equality sign. And this gives us the following. And let's say that we take the blue terms, so the terms that correspond to the object at a time t, we bring to the left-hand side. So we have x of t, which just remains there, and then we subtract from this 1/2 times v of t squared divided by a. And then all of the red terms, so the terms that concern the object in its initial position and velocity, we bring to the right-hand side. So we have x0 minus, again, 1/2 times v0 squared divided by a. And we arrive at this formula that describes the following. It's basically a conservation law of x and v. because we see that this specific combination of the position and the velocity of an object remains constant if we go an arbitrary time later, which basically says that this specific combination, the position minus 1/2 times the velocity squared divided by the acceleration, is something that is conserved through time. It is a constant. But of course, I promised you that we would be deriving the conservation of energy. So we still need to rewrite this conservation of kinematics, so to say, such that we find the terms E kinetic, which is 1/2 times m times v squared. And we, of course, already have this v squared and this 1/2. And for the potential energy, we would like to find m times g times some position x. Now, at this point, of course, we only have this position x, but we'll get there. And how to get there is, of course, to get rid of this a, this acceleration, because it nowhere appears in the conservation of energy or in the formula of energy at all. And to get rid of this a, we realize that this a is an acceleration of the object, which is due to a force that is acting on this object. That's what Newton's second law teaches us. An object only accelerates if there is a force that acts on this object. In mathematical terms, we have that a force will always cause a mass m to accelerate a acceleration a. Or in other words, the acceleration a is caused by a force F divided by the mass of the object. And I want to stress here that the force is an external force acting on the object, which will be important later on. At this point, however, we found our expression for A. We can simply replace A by a force divided by the mass of the object. And if we do this, we of course get the following. We have x of t minus 1/2 multiplied by v of t squared divided by f multiplied by m. And this is of course equal to x0 minus 1/2 times v0 squared divided by f multiplied by m. And at this point, we can of course multiply both sides of the equality sign by f, by this force, to get the following. We have this force multiplied by the position at time t, minus 1/2 times m times the velocity at time t squared. And this is exactly equal in the initial position. So we have the force multiplied by the initial position minus 1/2 times the mass times the velocity 0 squared. And what we get here is of course exactly what I promised you. It is the conservation of energy derived all the way from simply the kinematic equations. Because we see of course the kinetic energy both at time t and at the initial time. So this is simply the kinetic energy. And we have this term right here. Now you might wonder, well, is this really the potential energy that we're looking for? Well, yes, indeed, because the potential energy that we were looking for and that we all know is the gravitational potential energy, meaning that this F will be the gravitational force. Now we of course know the formula for the gravitational force, which is m, the mass of the object, multiplied by this gravitational constant. Now if we fill this in our description for the potential energy, then we see that we have m multiplied by g multiplied by x of t. And this is just a displacement which is oftentimes called h. So we get m times g times h, indeed the potential energy. And multiplying this equation simply by a minus sign, thereby switching the minus sign around, we get of course what we already know. We get that the kinetic energy minus the potential energy of our system at a specific time t will be equal to the kinetic energy minus the potential energy at a earlier point in time. So the total energy of an object does not change in time. Its kinetic and potential energy added together will not change and remain constant. This is exactly conservation of energy. To make these insights more tangible and easy to understand, let's go to a concrete example. And in this example, we're going to consider the case of an object with an initial velocity v that is sliding across a surface. Now for simplicity, this surface is of the same material and both the object and the surface also have the same temperature. And just to remind you, temperature is basically a measure for how fast the atoms in an object are jiggling. A high temperature corresponds to jiggling at a very large velocity, and a cold temperature corresponds to jiggling at a slow velocity. Now note that all of the atoms that are jiggling inside of a material are doing so in a random velocity, such that taking the sum of all the velocities at any point in time, they will all add up to be zero. If this were not the case, then the material will have a net velocity and thereby go somewhere. Now intuitively, of course, we know what will happen. Due to the force of friction between the surface of the object and the ground, the object will be slowing down and come at a halt at a specific moment. Additionally, we also know that the interface between the object and the ground will have heated up, so its temperature will have increased. So what has happened here? Let's first look at it from an energy point of view. We know that the kinetic energy of the object clearly went down because its velocity went down, and we know that the kinetic energy is equal to 1/2 times the mass of the object times the velocity squared. So if the velocity goes down and eventually gets to a halt, so zero velocity, then the kinetic energy will go down. However, we know by conservation of energy that this energy cannot just disappear. It needs to go somewhere. And where did it go in this case? Well, obviously it went to heating up the interface between the ground and this object. Basically, the kinetic energy was transferred to heat energy, the energy associated with a higher temperature. So kinetic energy was transferred from the object towards this interface into heat. However, this of course poses the same question as we started this video out with, namely, what really got transferred from the object to this interface? Are you able to point your finger to the energy that got transferred? Well, this is quite difficult. So let's try to make sense of this situation by only considering the motion of the particles. And to do this, we will of course look at the velocity of both the particles inside of the object and the velocity of the particles of the ground or the surface along which it is sliding. We know that since the temperature of the object and the temperature of the ground are equal, the random motion or jiggling of the atoms inside of the object and the ground are equal to each other. So then you might say that the atoms inside of the object and the surface have an equal velocity, but that is not exactly true, because we know that this entire object is also moving to the right with a certain velocity, and this velocity needs to be added to the velocity of the jiggling atoms. Therefore, compared to the ground, the atoms in the object will have a higher velocity. However, this higher velocity will have two components. The first component will be the jiggling, and this component will be equal for the atoms in the object and the atoms at the surface, because they are at equal temperature. However, the second component of the velocity of atoms inside of the object is an ordered motion. The fact that all of these atoms, even though they are jiggling in random directions, will all have a large component to the right. So this will be the ordered velocity. Now to see what happens at the surface and how the surface is actually increasing in temperature as the object slides across the surface, let's zoom in a little bit. And let's see what happens if a particle of the object at the surface collides with a particle at the ground. We know that the particle in the object has a very large velocity component in the direction that this object is moving, whereas the particle of the ground is just jittering in any direction with a low velocity. When these two particles actually collide, what happens is that a large part of this velocity of the object's atoms in the direction that this object is traveling gets transferred to the atoms at the ground, which thereby increase their jiggling velocity. And this results that the atoms of the object at the surface get a lower velocity component in the direction that the object is macroscopically moving, and the atoms in the ground will get a larger jiggling velocity component. Now this means that if the velocity of jiggling of the atoms increases, that the temperature increases, and that's exactly what we see at the surface. So if we now want to point exactly to what is transferred in this scenario, is that the ordered velocity of the atoms in the object is transferred into jiggling velocity. This means, of course, that the overall velocity of the object goes down, which is what we observe, and in place we get an increase in temperature, which is also what we observe. So what is really transferred is the type of velocity. It goes from ordered velocity to random velocity. And this is, in my opinion, a much more clear and concrete way where you can point to what really happens instead of talking about energy. Now, this was just an introductory video in the series about what energy actually is. And in the future, I will make a lot of more elaborate videos where I go into this concept more deeply. So if you're interested in watching them, consider subscribing. And with that, I thank you for watching and I will see you in the next one. Bye.